So with that, I'd like to introduce our speakers for today. We've got Louis Ryan, Principal Engineer at Google, primarily working on the Istio project and many others. We've got Idit Levine, the founder and CEO of solo.io, and Christian Posta, Field CTO here at Solo. Everyone, it's balls in your court now.
Hi, Betty. Hello. Good morning, everyone. I think it is going to be the one driving the slides. There we go.
Hi, guys. So I will start with a slide, and we'll start with first understand the first thing, which is what is the difference between control plane and data plane, and what are we trying to extend with WebAssembly? So let's first look at the two projects that we are all talking about. The first one is Istio, which is a service mesh coming from Google with a collaboration with IBM and Lyft. And the idea with this is the ability to actually have the ability to actually control the visibility, the security, and the routing for your microservices in your environment. In order to do this, basically Istio is taking what's called a data plane, in that case Envoy, and putting it next to any service that exists in your infrastructure. In order, when the request is coming to the proxy need to know what to do with this. And for that, we have the control plane. So Istio control plane is basically in charge to give all the information to Envoy in that case. And when the request is coming, Istio control plane is not involved whatsoever, and Envoy just will know what to do with this. Same thing exactly is going on with Glue. Just Glue is doing exactly the same thing, just is very focusing on the edge, right? So on the entry to your cluster. So the control plane is actually giving the configuration to Envoy, and on the actually runtime, when the user is coming with a request, Envoy just know what to do with this request. You know, to which service to route, you know, if it's allowed or not allowed to do this, and so on and so on. So we have the notion of control plane and a data plane. So let's understand a little bit, let's deep dive of how something like that is going to look. So in that case, I'm showing it with Glue, but it's really working exactly the same thing with Istio. And the user is basically giving me any configuration that is interested in it. In that point, you want to route to a service one, and you want to make sure that you're actually allowed to see this. So Glue responsibility in that case, and again, as Istio, is basically to configure the external server, in that case, the external auth server and the rate limiting server. They are global services. They need to be on the level of the infrastructure, and therefore, you know, they should not live in the data plane. And besides that, it will configure the data plane. And the way it's configured the data plane is basically this: it's configured that way that it need to configure what's called the filter chain. And the filter chain, what it means is that when a request will come, those requests is going to go through those filters. So in that case, the control plane is responsible to decide what is this order, as well of the filters, as well what is the configuration that each of them will have. So that way, when a request is coming to the user, it will go through all those services. Again, they will know what to do with this. And we'll make a decision if it will allow to go, and then go all the way to the upstream. And on the way back, it will do exactly the same thing and return the response. So what's beautiful about this system is that you basically can totally customize that. And you can actually add a filter to the chain and change the order of the chain, have the ability to actually customize that the way you want. So this is really powerful. And this is why Envoy is so special. The question is, it still creates a lot of problematic work to do this. For instance, every time that you're adding a filter, you need to write it in C++ async, which is pretty complex. The second thing is that after you're writing it, you need actually compile Envoy. And this is not an easy task at all. So there is a lot of you know, it's a really good, powerful technology, but there is a lot of limitation which is not as easy as we hope to do. So first of all, it would be very great if you can use any language and not just be forced to use C++. We want it to be as fast as it is right now. We really, really want it to be safe, that it will not take the proxy down. We don't want it to be needed to compile that again, and we want it to just to be very, very easy. So let's see how we chose in Glue to actually do this. And when we chose in Glue, we said that the thing that is most important to us is how fast or how efficient it in the data path. But what does it mean is that we basically mean that we are the one who need to write the custom filters, right, as the request to our customer, and give them a solution that is tailor-made to them. So we are writing the C++ filters, we are actually recompiling Envoy, and then we're basically giving it to our customer. So there is a lot of advantage for it, because it will be very fast and very efficient. It's really, really safe, but we have to use C++, which means that we need to, most of the time, we need to do the work. And besides that, and we need to compile it, and it's not really, really easy. So SDO decided to choose a different approach. And what they said is that it's really, really important to us that people will be able to write their own logic. And therefore, they created a component called Mixer. And the idea of Mixer is just a gRPC. So in the nutshell, in proxy, you have some filter that will know how to write to reach out to Mixer. And with Mixer, you will be able to basically adapt your own code. That way, you potentially can write it in every language, most likely people doing it in Go. And that's giving you a lot of the power, though it's coming with cost. Because that means that every time on the request part, the proxy need to send all the information that it have to Mixer. Maybe all they want to do is just modify the header. You still need to send all the body and all the information that it has to Mixer, and that's can cause potentially a problem. So you can use any language, though most of the people are using Go. So it is, there is a potential here. It is safe. I'm sorry, but it is very safe. Exactly as safe as running inside Envoy. There's no need to compile it, which is a huge advantage. And it is the developer experience is not the best it can be, but it's definitely easier than writing their own filters. So now, when we look at this, we felt that WebAssembly has a lot of potential to solve those problems. And now we'll move this to Louis, who will talk a little bit generally about WebAssembly, and then about WebAssembly and Envoy.
Yeah, good morning. So WebAssembly was a technology that we had been looking at for a while. Google actually does a lot of work with WebAssembly as part of the Chromium project. But we were looking at solving this problem of extensibility in Envoy, and looking for an embeddable runtime that we could use in Envoy that would give us the performance envelope that we were looking at, but also enable a much greater flexibility around the development model. So WebAssembly is as the slide says, a binary instruction format, effectively kind of like a bytecode format for a virtual machine. Right. So what you're embedding when you use WebAssembly is a little virtual machine that you can target with almost any compilation toolchain, and use with a wide variety of high-level languages, C, C++, Rust, but other languages as well, like AssemblyScript, and actually saw an example yesterday using Go. And WebAssembly isn't just for the web. The creators of WebAssembly, while they primarily worked on solving, creating an embeddable runtime inside browsers, they designed it in such a way that it would be equally applicable to embed in other types of environments. Because it's born from the browser world, we had to make sure that WebAssembly was portable, right? It has to run on every major operating system and platform that these major browsers work on. So a lot of engineering effort has gone into WebAssembly over the last several years to do this, and you'll find support for it basically in the runtimes provided by Chrome, which is the V8 engine. In Mozilla, they have an implementation. Windows Edge obviously is now using Chrome, and WebKit also has an implementation of WebAssembly. So all the major browser platforms support WebAssembly today, which means that there's really, really good cross-platform support. The other thing that it enables, because it's this intermediate form, right? You, the developer, when you write WebAssembly code, you take your code and you compile it to the Wasm bytecode format. And then that same code will run anywhere that there's a WebAssembly runtime, right? And a matching environment. And so this is what this diagram is showing you, right? I don't target any specific hardware platform anymore. I target the WebAssembly output format, and then the WebAssembly runtime will make sure that it runs in those environments. Next slide. WebAssembly also has a couple of other pretty impressive goals that they were looking for. Because it's designed to run embedded inside web pages, you know, your average web browser today is opening web pages from lots and lots of different places. And so all these different programs running inside your browser, right, you have to make sure that they aren't able to interfere with each other. We're all probably pretty familiar with all the different forms of attacks that have been performed against web browsers over the years. So you want to make sure that all these applications, which are, you know, in some cases quite low level and highly performant applications, aren't able to attack each other. So what WebAssembly does is it defines a sandbox for the application that is very well bounded. It provides this kind of what they call a contiguous memory region boundary. And the runtime will load the application into this block of memory, and the application cannot access anything outside that block. The only thing it can do to talk to the outside world is to talk to a well-defined interface exposed to it by the environment. So this allows you to take, you know, what might be a very risky application and not give it access to anything. You know, don't give it access to the network, don't give it access to anything on the screen, run the application and have a very high degree of confidence that it's, you know, no matter what, you know, malicious intent it has, it can't escape its sandbox. And this is really important for the web, and it's also going to be important, I think, on the server side, and we'll get a bit more into that. You know, WebAssembly was primarily envisioned, you know, to make sure that we could build high-performance applications in the web. And so its primary competition in that realm is JavaScript. So when you run a JavaScript application in the browser, and there are some pretty big, complicated JavaScript applications, whenever you load up the JavaScript code, it goes through these different phases, right? It gets parsed, it gets compiled and optimized and re-optimized and then executed. And because it's JavaScript, there's also memory management that's handled by garbage collection. So, you know, a lot of work has gone into JavaScript engines over the last decade, and JavaScript has become pretty fast, but it still cannot compete with direct compiled, highly optimized native code. Because WebAssembly goes through this compilation phase, you know, similar to what you would see with something like LLVM and Clang, the decode phase is much shorter because the format is binary. The compilation phase really just means the just-in-time compilation phase where the WebAssembly runtime converts the WebAssembly bytecode format into an optimized form for the specific hardware platform, and then it executes it. And so what you typically see is programs of equivalent complexity in JavaScript and WebAssembly. WebAssembly loads much faster, compiles much faster, and executes much faster. In fact, if you look at benchmarks today, you know, if you take an equivalent, you know, fairly simple C++ application, compile it to your native platform, compile it to WebAssembly, and then benchmark them against each other, you'll often find that WebAssembly comes in, you know, no more than 10 or 20% slower than that C++ application, which is pretty impressive, right? That means that the compilers are doing a good job and the runtimes are very, very efficient. So you can get this almost native performance, and you know, we expect to see as WebAssembly evolves over the next few years that we'll see that gap close, and the situations in which that, you know, where that gap is wider become less and less common as people do a better job with optimizations. But you know, for the most part, you can kind of assume that WebAssembly runs at near native speed, and that's a really important thing when we start talking about networking. Next slide. The other thing, because WebAssembly is this kind of intermediate format, this what we call an intermediate representation, you can focus all the different compiler tool chains to produce that intermediate representation, and then the runtimes, which are bound to any specific hardware platform like x86 or ARM or MIPS or the N other platforms people could be using, right? It makes the compiler toolchain simpler to reason about, right? They focus on producing that intermediate representation, that WebAssembly bytecode format, as efficiently as possible. And then the different virtual machine implementations for WebAssembly focus on producing the most efficient binary executable form on the given hardware platform. So this is pretty typical for most platforms today. If you're familiar with Java, Java works in a similar way, but Java doesn't have as efficient a compiler toolchain, right? Java, the representation, the intermediate representation is still pretty abstract from the hardware platform and from what the actual code might do. The intermediate representation in WebAssembly is much more low level. It's much more like an assembly language. Okay, next slide. So while WebAssembly, given its name, was very much focused on the web in its early iterations, the WebAssembly working groups, as part of the W3C and among the major browser vendors, have been well aware that WebAssembly is also a very suitable platform for running systems. And so one of the first things that happened when people were considering using WebAssembly outside of the web use case was what might it take to run WebAssembly modules as if they were system programs. And so, if you're familiar with Linux today, right, most applications, when they're compiled, they compile down against the Linux binary ABI. And so if you want to do something similar to that, you need to produce an ABI specification, right, that lets a WASI program or WebAssembly program access features of the operating system, like files, network, process, connect to I/O and low-level systems, et cetera, et cetera. So they decided to form a working group known as WASI, which is the WebAssembly System Interface. And they are currently working on standardizing an ABI for WebAssembly programs to interact with features of the operating system. And you'll start to see runtimes and demonstrations of this being used. And there are, in fact, I think even examples of people using WebAssembly and WASI to run WebAssembly modules as Kubernetes pods using the same platform. So while we were looking at, primarily at a networking use case, others in the ecosystem were looking at using WebAssembly for more for system processes. And so, having done this research, we said, I think it makes sense to embed a WebAssembly runtime in Envoy and then provide a very kind of networking-oriented ABI for WebAssembly modules to interact with the data plane in Envoy. So we started doing some prototyping and figuring out if this was possible, and it became clear pretty quickly that it was. And so we committed to embedding a WebAssembly runtime in Envoy. Coming from Google, our first choice was to use V8. V8 is widely used in Chrome, which is extremely widely used. We know the team quite well, and it has very good performance characteristics. So what we wanted to be able to do, is any of these kind of functions that it had showed you in the earlier slide, instead of having them to be compiled natively into Envoy, which can take quite a bit of time, it's a long and complex build process, we wanted to be able to say, look, you can have a Wasm module, and then you can tell Envoy, just load this Wasm module and have it perform this filter action or some other action inside Envoy. So we did the embedding. We took V8, we embedded the runtime inside of Envoy, and then we made sure that you could implement modules in WebAssembly against the Envoy ABI, and then load them dynamically into the Envoy runtime, right? So you can take a stock build of Envoy, and tell it using the control plane to load up a Wasm module. And then that Wasm module now will execute in the data plane of Envoy. And you can do this dynamically, right? You don't have to redeploy Envoy, you don't have to restart it, right? It can be done completely on the fly. And these Wasm modules can do whatever you want, right? They can do the same set of things that the code compiled natively into Envoy can do for the most part, right? I can implement a rate limiting module in WebAssembly. I could implement something that does a protocol transformation. I could implement something that does an authorization check. So we effectively have this working at kind of an alpha level today. And we're working very hard to get this to what we would consider a beta or production quality, hopefully in the next release or two of Envoy. As I mentioned before, we're using V8 to do this. And V8 performs pretty well, and we'll publish benchmarks about the relative performance of running WebAssembly modules inside of Envoy. But so far, in the Istio project, we actually implemented all of our telemetry exporting so that it could either be compiled natively into Envoy or loaded into Envoy as a WebAssembly module. So we actually have the ability to switch back and forth. And so far, we've been pretty happy with the relative performance difference of running the code in WebAssembly or running it as natively compiled code into C++. We see some performance degradation, but not enough to actually be meaningful to us. And the flexibility that it gives us in terms of the ability to load and reload modules dynamically and to use stock certified builds of Envoy is very powerful. Next slide. So we talked a little bit about what the ABI is, right? The ABI is really an interface that Envoy exposes to the WebAssembly module to allow it to interact with the flow of data through the proxy. All right, so here's an example of a method that Envoy will call on a WebAssembly module, and this is kind of shown using C++ syntax, saying, look, I've received some HTTP headers, do whatever you want with the headers and then tell me what to do next, right? So Envoy is calling into the module. And you can mutate the headers, you can remove headers, right? You can tell Envoy, I want to reject the request, right? I want Envoy to start processing the body, right? These are the types of interactions you can perform. These ABIs tend to be fairly low level, right? If you go and look at the ABIs for Linux, for instance, right, they're very low level things. So typically, if you're going to have a developer community sitting on top building plugins for Envoy, they'll probably want to be using an SDK that provides a nice level of abstraction above this ABI. And so what we've done, Google and Solo, we've worked on developing SDKs in C++, Rust, and AssemblyScript, which is like it's a variant of TypeScript that should be pretty familiar to most people if you use TypeScript before or any form of typed JavaScript. AssemblyScript will look very natural to you. And as I mentioned earlier in the talk, there's actually an example, somebody in the community just developed one for TinyGo, right? So you can basically build an SDK in any language that will work with the existing WebAssembly compiler toolchains, and then use that SDK and build modules and deploy them. So now, we have the ability, to take one of these SDKs, start writing a plugin there in the language of choice, compile that module down into the WebAssembly bytecode format, and then using one of the control planes, whether it's Glue or Istio or some, directly configuring Envoy or some other Envoy configuration, push these Wasm modules into running Envoys dynamically. So what do we get out of this? Well, we can use a much larger variety of languages than we were able to use before, right? Pretty much anything that works with the LLVM toolchain today will work with WebAssembly. It's fast. The bytecode format is very efficient, and the existing runtimes that implement these virtual machines, get close to near native performance. We have safety because of the memory sandboxing model and the guarantees that those VMs provide. And when the Wasm module is loaded into Envoy, the compilation step of converting the bytecode format into the native format is very, very fast. And similarly, I also don't have to recompile Envoy every time I want to make a change, which is a much larger compilation thing. So now the only thing that's left to be done is to make this easy for developers to consume and for operators to kind of push out modules and experiment with them and manage them in production. So I think at this point, Christian is going to take over and talk to you a little bit about the developer experience and maybe a bit of a demo.
Yeah, I mean,
yes. Oh, go ahead.
Yeah, go for it.
Oh, Edith, you were going to have some words to say here.
I'm
and I'll take
supposed
the
to do
demo.
this. Yeah, exactly. Christian will do the demo, but before that, I just wanted to say that when we look at all the work that Google is doing and wanted to help, the thing that was really, really clear to us is that this is a very amazing technology that it's will power a lot of people to do whatever they want. That will create the experience to our customer and make it really, really easy for them. But then I saw this tweet from Solomon Hayek. And what I realized is that there is a lot of similarity between what Wasm and Wasm is doing to basically what Docker did before, right? I mean, in the nutshell, it's a sandbox. It's giving you the ability to run it safe and fast and whatever. All this, the problem that Docker basically tried to solve, in a way, can be solved by Wasm. So when I look at it, I said, this is great. But then what if we can bring all the amazing experience that Docker brought to Linux container and brought it to Wasm and specifically with to Envoy. So this is why we created WebAssemblyHub, and that was really inspired by the Docker Hub and the Docker tools, which is basically the ability to make it very, very simple for someone to build a model. Again, we hide all the complexity behind the scene, and there is still quite a lot of complexity. You will be able to publish it, first of all, for you to consume it later, or for even people from the community who will be able to share exactly like Docker Hub is doing. You'll be able to discover if you didn't build one and you just want to get one that someone else do, you can totally discover that. And then you can actually also, one more step that we did a differentiator from Docker is the fact that we're also deploying it automatically on those platforms. So right now we're supporting Glue, we're supporting Istio, and we're also supporting local Envoy. And that's mainly for debugging your extension and make it very easy to use. And now I think that we really achieved everything that we wanted. You can use a lot of language, it's fast, it's safe, it's not need to compile, and it's easy. And now Christian will show you a demo to see how easy it is.
Yes, I will. Let's share my screen. You all should be able to see my screen now. Hopefully, okay. So if you go to WebAssemblyHub.io, that'll take you to the landing page of the registry, where, as Edith said, folks can build their own WebAssembly modules and push them to this registry and share them with the wider community. So you can come here and you can search for a particular interesting piece of functionality that you might want to deploy into an Envoy-based service mesh or API gateway like Glue and Istio, and then from there you can pull them down and deploy them into those particular pieces of infrastructure. If we click on the docs link here, that will take us to a set of tools that can be used to automatically create or bootstrap these WebAssembly projects in various programming languages, the tool chains to build and publish the modules. If you click on tutorials, we have, so for example, in deployments, we can see how to deploy into various Envoy-based frameworks. What we're going to look at in the demo today is how to use the WebAssembly Hub with the Wasm tooling that comes along with the WebAssembly Hub and deploy WebAssembly modules into Istio, and specifically Istio 1.5. Again, I want to caution that this is still alpha level, but it's, as Louis said, coming along pretty quickly and should get into beta and more GA status fairly quickly. Istio 1.5 announced a few exciting things about the project, but you can come into the 1.5 announcement and read more about the WebAssembly mechanisms for extensibility. And if you look at all of the posts in the Istio blog, there's quite a bit of exciting information in there. So from here, let's get right to it. We're going to be taking a look at the book info app, as one does when demoing Istio. And we're going to be looking at the communication between the product page here and the details service in the backend. And so we're going to look at the calls between those two services, and we're going to create some new WebAssembly modules and inject that into the Istio sidecar service proxies so we can alter the behavior of the network requests as they go over the network. So let's not go there, let's go here. And we're going to start off, this is a live demo. I do have a little helper script here to help me type things, as you know, at times might be inclined to mistype things, but hopefully the script will help. The first thing we're going to see is that we have an Istio 1.5 deployed. We can see that because the control plane has been built using the new Istio D functionality. We'll also take a look at a running book info sample with the Istio sidecars injected. And we'll also take a look at the call between the product page and the details service. And I've done this in verbose, but we can see the output here. We can see that it was returned successfully. And we can also examine some of the headers in the response. And the reason we're showing that is because in the WebAssembly module that we'll build, we'll do some manipulations with that. First thing we're going to do is use the WebAssembly or Wasm tooling to bootstrap a new WebAssembly module. So if we do Wasm init, we'll call it filter. Right now we see C++ and assembly script as options. Shortly we should have Rust, and as Louis mentioned, there was some folks showing off TinyGo. Hopefully we can get TinyGo into here as well. We're going to choose assembly script, and then we're going to choose which Envoy-based frameworks that we want to target in their versions. And this becomes important because we want to, behind the scenes, make it easy to wire up the correct ABIs and SDKs to the version of Envoy that you'll be deploying into. So we do that, and that should create our project. If we open our project now, we can see that it has automatically generated a few descriptor files. If you're familiar with TypeScript and Node.js, you can see that it has added to the dependency chain or dependency list here the correct SDKs and ABIs. If we come here, we can see the exact versions that we're targeting, and it has automatically generated a source code file that you can then use to implement the functionality that you want in the WebAssembly module. So in this, the skeletal structure here, we can see that we're calling, or we're overriding the onResponse headers function here. And what we're doing is, if we have some configuration, then we're going, if we don't have configuration, then we'll just add the hello world header. If we have some configuration injected in, we'll add hello and then the value of the configuration, which means not only can we make code changes here to add and change functionality as the request gets processed in Envoy, we can also inject configuration into our module to have it behave differently depending on how we configure it. So let's just go ahead and build that WebAssembly module. We're going to do Wasm build assembly script and give it a tag. Give it a tag name just like we would with Docker, right? So Edith mentioned that we're trying to have a nice developer experience, and we've modeled it out of kind of like Docker. So this ends up building an OCI image with the WebAssembly module and descriptor files in it. Actually, if we come over here, just quickly go off script. If we look at the store here, let's do, so this is what was built locally. See, this is why I script the demos. This is what was just built, this image right here. And if we take a look at that, we can see what's included in the image. We have the Wasm binary. We have the runtime config, which points to the different ABI versions, and a descriptor file that kind of pulls together, and all of this kind of pulls together a spec for what the WebAssembly module that we publish would end up looking like. So that's all good. Let's now, so WASM list, we can see our demo add header v4 was just added. And the last thing we're going to do is push this to the WebAssemblyHub, crossing our fingers. Things that go over the wild network, you never know. Looks good. And now let's come back to the WebAssemblyHub and log in. Let's log in as me. Hopefully I remembered my password correctly. Don't save that. Now under demo add header, which is the image that we just built, under tags, we can see our new, the new tag that we just created and pushed. Now this is, if we click over here on Explore, we can see all of the different WebAssembly modules that folks have shared, and ours would be included in there. Well, there's gonna be a lot of them, but here's the one that that I just pushed. So that's, and we can search it locally from the CLI. That looks fine. Okay, so now we've pushed and we've allowed folks to discover the WebAssembly module. Now let's part 2. Now let's take that, pull that down, and deploy that into Istio. So just did that. What we're going to do here is we're going to run wasm deploy. Now wasm deploy, well, all right, let's make sure that we can still call our product page to detail service and see we don't have any extra headers. We don't see the hello header in there yet. Wasm deploy is going to allow us to very quickly deploy the filter or the WebAssembly module that we want into, in this case, Istio. We could have also have chosen Glue as an API gateway built on Envoy, or Envoy vanilla directly itself. And what we're going to do in this particular case is inject it into all the workloads running in a particular namespace, but we can also be very surgical or very specific about which workloads should get this WebAssembly module by specifying a selector to select which labels will receive the WebAssembly module and have that injected. So let's do wasm deploy. Let's do the tag and the image that we just created. And what we should see that it's doing, hopefully correctly, it'll pull down that WebAssembly module. It will cache it locally into the Kubernetes cluster, and then, oh, that didn't look too promising. Let's, oh, no, it is, okay. Just momentary heartache. It looks fine now. So what it's doing is pulling it down and deploying it into Istio and configuring Istio's sidecar proxy to use that particular WebAssembly filter. If we look at in Istio, the way to do that is to configure using an Envoy filter. It's sort of a way, it's part of the control plane to give overrides to override the specific configuration that you want to give to the Envoy proxies. We see that it created that filter for these different workloads, all of the ones in the book info namespace. If we look at a particular filter, we can see exactly what it's doing. It's creating a WASM filter that will use V8 and is loading, in this case, the Wasm module off the file system, which got injected in there. We have an update to WASM that should, it's in pull request, we're reviewing it right now, that will update it. So we don't actually do it over the file system, but that we stream the module directly to the Istio sidecar proxy, and we don't have to mess around with this. But this is, in this particular demo, how it's working. So now we see that everything is up and still running. Let's make the call between book info product page and the detail service, and we should see our new hello header, and we do. And we've configured, if you'll notice, if we come back here to where we deployed it, we passed in a config of tomorrow, which, if you remember back in the source code where we did that if statement, we're going to pull the value dynamically depending on how we configured the WebAssembly module and display that as the value for our hello header. Now, this was done using the WASM tool directly. This could be a nice quick way to do this in development, but there's also all right, we can undeploy it. An approach to doing this using a declarative syntax and a controller that is described in this blog, one of these blogs right here on Istio, where instead of using the CLI tool, you define a CRD that defines the various parameters of the deployment and where to inject the WebAssembly module, and then at runtime this happens using a controller. So this is something that you could have in your GitOps pipeline and so forth, and not depend on the CLI. So that's all I had to show. Go check out the Istio 1.5 release. Check out the ability to extend it, and then check out the WebAssemblyHub for a simplified and easy way to get started with building WebAssembly modules for Envoy and Istio. So I think at this point, we can bring the rest of the panelists back in and take questions.
Great, thanks everyone. So folks on the webinar, please at this time, go ahead and type your questions into the Q&A window or the chat. Louis, thank you for answering the two of the questions that came in through the Q&A, but I think it might make sense for us to kind of like
to do it
just
verbally.
read them out loud and kind of discuss the answers to see if folks have additional follow-up questions to that.
Yeah, so maybe I can cover the first one from Jonathan, which is, what types of extensions will be possible, or what is the limit to to what WebAssembly can provide in terms of extending Envoy? Given WebAssembly's pretty impressive performance envelope, there's not a huge amount of limit, but there are some probably pragmatic choices that we'll be making in conjunction with the Envoy community. Envoy being a proxy, probably 90% plus of the traffic that it sees is TCP or HTTP, or one of the kind of common HTTP variants. And so it probably doesn't make sense for kind of fundamental, common, low-level protocol handling to move into WebAssembly modules. But there are a lot of extensions that are already built into Envoy that are not ubiquitously used. Like if you go and look in the Envoy documentation at the filters that have been added, right? They've added filters for kind of bespoke RPC protocols. There's just a lot of other filters that are built into the main line of Envoy. And in talking to the Envoy maintainers, right, they would like to get out of the business of shipping all these extensions built into their pre-built releases. One, it makes their lives easier, right? They don't have to review all of these things. They don't have to be responsible for them. It makes Envoy itself more secure because it's less code, right, that has to be subject to the amount of scrutiny that Envoy itself is exposed to because of the important role it plays in the network. So I'd expect to see a lot of those kind of non-frequently used filters move out to WebAssembly modules. And I gave some examples in the Q&A answer. And there's a lot of consensus within the Envoy community that this is something that should happen. And given the performance envelope, there's not really an awful lot of downside to moving some of these protocols out or these other filters out. We did that for telemetry with Istio and have been pretty happy. And telemetry is a pretty fundamental thing to be doing in any data plane. So I don't see there being a lot of impediment. Now, WebAssembly implementation has to mature, and there are other types of optimizations we'll probably have to do, but in the long run, I think you'll see most modules move out, and only highly standardized, highly used protocols remain in the proxy.
The other question here is when will the Wasm SDK for Go be available?
So on that one, we don't have an immediate timeline. Certainly there's not somebody on my team currently actively working on it. But Go has pretty good support for WebAssembly, but there are a few limitations to using Go. And because Go is a garbage collected language, you need good runtime support for garbage collection to make this efficient, and which is why we focused on C++, Rust, and assembly script first, because they don't have that requirement. But there is a variant of Go called TinyGo, which is not garbage collected. And there was a tweet yesterday from somebody in Japan who had developed an SDK and gotten it working with the Envoy ABI. And so I expect, we'll probably see that come out quite soon. And once the WebAssembly VMs pick up garbage collection support, which is on their roadmap, then I think you'll see first-class Go support. But for the types of code people are likely to be writing in Go, TinyGo is actually probably going to be a pretty good option. Right? It's the Go language. There are just some things you're constrained from using.
And that's a good, that's actually a good segue to the next question, which kind of brings that topic together along with some other aspects is, can I use TinyGo to write filters that can be used in Glue? One of the things that, Edith, that you mentioned was that with the Wasm support for Envoy-based solutions, and Glue being one of them.
Yes, so in Glue we're supporting, whatever is in apps in Envoy we are supporting. As Luis said, there is no yet SDK for TinyGo, and it's not supported yet. Once it will be supported, we will bring it to Wasm, and it will automatically support Istio, Envoy, and Glue. So we will be able to run it. But today we're supporting in Glue the same thing that we're supporting in Istio, which is assembly script, as well as a C++, and Rust is coming very, very soon.
Yeah. So this kind of speaks to the power of WebAssembly, right? If somebody out there built an SDK for Fortran, let's say, then as soon as that SDK was working and the compiler toolchain for it was working, then everything downstream of that would work, right? From WebAssemblyHub all the way to the Envoy runtime and live deployment, right? So that's that layering, that separation that we talked about earlier. If you go to the WebAssembly organization, they have a list of languages that have existing compiler toolchains that support it. It's about 60 languages right now. We're not going to take on trying to add support for all of them, but the community could certainly very easily write an ABI binding for an SDK for any one of those languages and get it working as an Envoy module.
Yes.
So there aren't really a lot of restrictions there.
Right, and Solo will help as well. So I mean, if there, it will be great to get from the community the request of which language they're interested in, that we will be able to actually prioritize which language we're working on next.
There's a question here on asking that if they understand correctly, the filters are set up on pod ingress. And the question here is, can they also use it to do egress?
Yeah, so the example ABI that I showed and that Christian kind of showed you in the example was just one piece of the API surface. There are APIs or callbacks effectively that occur that go into the module for the response side processing of HTTP, or if you're writing a module that needs to interact with TCP, then you would interact with data passing out on the response side. So both sides of the flow are covered.
Yeah.
Great. Any other questions out there? And thank you to Jonathan for posting in the chat and sharing with all the attendees the list of languages supported by WebAssembly.
Right. I would just add that, guys, we are on the Slack of Solo Slack, and I really recommend you guys to join. There is a lot of Wasm, there is a channel called WebAssemblyHub, and there is a lot of a lot of people that are actually very interested in this and writing. And as a community, I think we can do crazy stuff. So please join the Slack, I think, if with any question or any request.
Yeah, and if you have lower level questions about the Envoy integration, or you want to write an SDK, or have questions about the ABI, or how you could contribute to the support of WebAssembly and Envoy, that discussion is mostly right now happening in the Istio Slack, which you are also very welcome to join.
Mm-hmm.